I am so happy to have Mark Arundell back again with us today. So Mark is the principal geologist at IMEX Consulting with over 30 years of experience, dominantly as an exploration geologist throughout Australia and overseas. He has multi-commodity experience in precious, base and industrial metals, and it is going to be amazing hearing from him today about does resampling create value, developing a geochemical exploration model for the Golden Grove VMS in Western Australia. So it's going to be an awesome session. Please keep using the chat and we'll open up the floor at the end. And thank you so much, Mark. It's awesome having you. Thank you.
My pleasure, Jess. Look, thanks to GeoHug and once again to Jess for the opportunity to talk on GeoHug. It seems to be an annual event these days. And yeah, look, really looking forward to presenting this work. And I really want to acknowledge Luke for his geological insight. That's what basically made this whole thing fly. And also to 29 Metals Golden Grove for the permission to present. I'm on Wiradjuri lands here in the central west of New South Wales, and our house is on the beautiful slopes of Garnabula, which is also known as Mount Canobolas. So just for a little distraction, I don't know whether everyone actually saw this, but it's just worth it just to see Jess's expression at the moment. It's great that someone recognises someone's wonderful contribution. And I think we'd need to send a note to Jess's dad to clear some space on the mantelpiece or open up the doors to the pool room, because there's a bit of a trophy there that looks like it'll have to move a few things away. I'm not exactly sure what a new professional is, and hopefully Jess can give us some insight on that at the end of it. But definitely GeoHug has been a notable achievement and has provided a great service. There were some other words there, but I thought Cat Wrangler for GeoHug was a bit more of a accurate description. And it is no doubt that GeoHug over the last couple of years has contributed greatly to geological knowledge globally. And yeah, having guys like Cam and Mike is definitely worthwhile in terms of improving people's mental health. So big yell out to Jess here. And I did see one thing of applause there, so hopefully we can find a few others sometime during today. Okay, on to the reason why we're here. Is resampling useful? So it'd be good if we can just find out whether people have done it recently. If you want to just perhaps put something into the chat or let Jess know. She can actually give me some sort of idea when we get to the end of this slide whether people have actually done it. And another question, you might want to put it two next to this one, was would you do it again? Perhaps not the way that these people are actually splitting their samples, but there are other ways to do it. And during today's session, I'd like you to think about why you have done it. And the other thing is, did you actually learn anything from it, and was there value? So today I'm going to talk about some work that was done at Golden Grove. The initial cost of the work was in the order of about $10,000. So to develop a geochemical model for exploration, and let me just say it was a ruthless exploration model, is actually relatively cheap. So Jess, were there any numbers there? You got a rough idea of how many people have done it?
Yeah, about 5 or 6 so far.
Cool,
7.
That's all right.
A lot of them have been core. Some have said soils, extremely useful, high value, yes and yes. They're the sort of answers coming through so far.
As long as there are no no's, that's all we want to see.
No no's yet. No no's yet.
Cool.
They're not admitting it.
Right. Just as I like to say to my children from time to time, I'm starting to believe I'm seriously old. This is a photo from my first drilling campaign in March 1986 at Mount Magnet in Western Australia, which is about 600 k's north of Perth. You can see things have changed significantly. I think the only safety gear the guys have got on is a pair of boots, basically. I do love the toweling hat on the offside of there. So we were doing what's called rotary air blast drilling, which is a bedrock sampling technique, drilling under cover, and maybe I should have put cover in inverted commas there. In 1986, the only thing we sampled was the bottom of the hole, and my instructions were if I hit any quartz veining, I was allowed to sample that as well. We probably only analysed for gold. Honestly, I don't remember, and this term regolith just basically didn't exist. So the table underneath there is a comparison of 1980s detection limits and current detection limits. And the change there is orders of magnitude. It's not at times, it's actually how many orders of magnitude. So our detection limits have seriously changed. We've gone from 5 ppm in the 1980s, say for business, to 0.01. And people wonder why we're seeing things in rocks that we never saw before. Well, basically, I think it's mainly a function of the fact, one, we're looking for it, and two, we've got great pieces of kit that can get down into that level. So why would you do it? I mean, okay, maybe in the 1980s, we were looking for direct detection of mineralisation, drilling straight into the ore body, or maybe just trying to get into the low-grade halo. But these days, with the advent of these new techniques and a lot of work like Scott Halley and others have actually done, we're actually starting to see what I would call real footprints around mineralised systems. And then 3 sort of things we can talk about with these low-level detection techniques are pathfinders, alteration, if that's actually available in fresh rock, and also lithogeochemistry. We can actually have a good guess as for what the rock type is, even if it's extremely seriously weathered. And I suppose this is what I like to say to people, you know, I know when I've intersected ore, I know what ore looks like, but I'm still really wondering what a near miss looks like. And some of this stuff that Scott has been involved with, where we're actually seeing signatures in elements that probably weren't recognised, particularly not in the 80s, in elements such as maybe tin, but probably more so in bismuth, tellurium, and antimony and thallium. It's largely driven by the fact that we're actually starting to see detection limits down at that sort of level. This one here is basically to remind me that the fluid flow zonation isn't just vertical, that we actually see lateral characteristics with it as well. So if we're actually looking in this case at porphyry, or I prefer to say an intrusion-related system, we'll see that even though down the bottom on that right-hand side, the 0.5% copper footprint might actually be relatively small, once we actually get into the realm of bismuth and tellurium and say even antimony, the actual footprint of these things in the planned sense is actually getting quite larger. Anyway, that's just a bit of an intro before we actually jump into Golden Grove itself. So Golden Grove is located about 400 kilometres north of Perth. It's an Archean VMS copper and lead zinc system hosted by predominantly felsic rocks, and it was discovered in the early 1970s. There's mineralisation, significant mineralisation at 3 deposits: Scuddles, Gossan Hill and Gossan Valley. It actually came into production in 1989. The Scuddles deposit is on the right-hand side there and extends down to about, or just looking at my scale here, probably about 1.8 kilometres, and it's about 2 k's north of the Gossan Hill deposit. Current mining area at Gossan Hill is basically in the Xantho area. And about 7 k's to the south of that is the Gossan Valley series of deposits. So, mineralisation actually occurs at 3 discrete horizons in the stratigraphy, and all of those are near the contact of the Golden Grove Formation and the Scuddles Formation. So that the orange dashed line that I've got running through that slide is critically important to where mineralisation is developing over this whole field of about 30 odd k's or 37 k's, I think it might be there. The rocks can be weathered up to about 100 metres in depth, particularly at the southern end, and transported material can be up to about 70 metres thick as well, down on that southern area. So in the last 20 odd years, I could say historically, because 20 years is getting to be quite a long time, a lot of the exploration has been focused on geophysics, and there'd been relatively limited recent geochemical exploration. So 3 things I just want to mention on this particular slide is if you told me 20 years ago I was going to be giving this talk, I would have questioned your sanity. Basically, at that time, I would call myself a VMS mounder. I did not actually believe that you'd actually have some sort of hanging wall to a VMS system. And when Bruce Gemmell suggested doing a project looking at hanging wall alteration at the Hallier project, I think my words were, Bruce, that's going to be a waste of time. So I actually owe Bruce an apology. These days, I basically believe that if you're going to have a decent VMS deposit, it's probably better if it's a subsea floor replacement style. And with that, you're going to get some sort of decent hanging wall alteration with that. Now, just to get people in the right sort of orientation, this is probably how your original VMS formed, but at Golden Grove, I mean, it's Archean, so it's allowed to be a little bit deformed. We've actually just basically turned everything about 90 degrees on its side. So when I'm talking about hanging wall, I'll be talking about rocks on the left-hand side, footwall with rocks on the right-hand side, and if you like, our stratigraphic facing is up. And just one thing I'll throw in here, because I know that there are some people who'll be very interested. One of the things I find interesting about all these diagrams is that there aren't any faults or structures on them. So why would you want a geochemical model? And as I said, the Golden Grove tenements cover about 37 kilometres of prospective terrain. There's no mineralisation in there, 3 deposits, 2 current mines, and most people might consider it to be well explored. There's over 40 years, almost 50 years of exploration. Geophysics has been applied throughout the leases. The most recent most recent program was a downhole EM survey, which was not particularly effective in delineating any new mineralisation, but that's more of a function of the conductivity of the material that you're chasing. There's some excellent detailed maps, regolith and fact mapping being completed over the area, and that's been augmented with bottom of the hole RAB geochemistry, geology, which helps fill in a lot of the gaps. And there's over 10,000 drill holes of basement samples there. I wouldn't say it's an issue, but the reality of that is that a lot of that drilling was done in the 1980s. And at that time, generally the suite that was analysed for by atomic absorption spectroscopy would have been copper, lead and zinc. And you get a little bit of silver and gold analysis with that. Now, as a mate of mine, Bruce Mowat, used to refer to it, we can do pandemonium. 48 elements for probably a cheaper cost than what we were paying for that elemental suite of 4 plus gold back in the 1980s. Of those elements, the major ones, I've just highlighted copper, lead, zinc and silver. The detection limits haven't significantly changed, but it's actually the range of elements that we can actually get now that is much improved. So I've mentioned the pathfinder signature that we might be seeing in a porphyry style system. In the advent of this 4-acid digest ICPMS, we're seeing things like thallium, antimony, bismuth, tellurium, and say tin in the VMS systems. So if we have a subsea floor replacement style VMS deposit, it's probably no surprise that we're going to see elements maybe we haven't recognised before, like molybdenum or arsenic or bismuth, antimony. I actually haven't shown these in any particular order. I'm just saying that these things we can now start recognising in the hanging wall. So the program of resampling at Golden Grove involved about 280 samples. Roughly, the idea was to try and get about 100 samples from each of the known deposits, basically to characterise each of the deposits. These samples were mostly 30 to 40 years old, and I think that's a great lesson on why we shouldn't be throwing out old samples. Basically, they have an enormous pulp store there, and the guys were able to go back and find the original pulps, split them in half, and actually then send it off for reanalysis. And that was done with the 48-element geochemistry. And we'll use the term MEG for multi-element geochemistry of these bottom of the hole rotary air blast pulps. So just to give you an idea of what type of product you can actually get out of that. You'll see there's a black line. If we just look at the top left-hand corner there of the molybdenum plot, a hanging wall is on the left-hand side, the footwall on the right-hand side. There's a surface projection of mineralization sort of running up the middle of each of those plots in that black stick there, if you like. So you can see that in the hanging wall, we're seeing a signature of molybdenum, indium, and bismuth, and also a few other elements in through there as well. So some of this is weathered material, so some of it will actually be a little bit iron controlled, but probably the main thing to note out of this is the fact that we're actually seeing more of these elements actually sticking up into the hanging wall than we do in the footwall. And part of the reason for that, I think, is there's a lot of fluid that's gone through the footwall. And so things are a little bit more messy, shall we say, there. So a geochem model for Gossan Valley could be thus developed. You can see in green there is an outline of the zinc shells. The light blue is the copper shell. On the left-hand side, I've got the hanging wall dacite unit through there. I should point out this side, you may have noticed there's been a rotation of the maps because the mine grid is about 50 degrees east from true north. As I mentioned, the yellow is the interpreted or mapped, more particularly can be mapped in some places, hanging wall dacite in the yellow. And you notice that the pathfinder signature, which I've labelled there in orange, is sitting within the hanging wall itself, basically proximal to the mineralisation directly above it. Now, occurring just to the south, we're seeing this distinct lead-thallium association, which appears to be more associating with the zinc lenses, which sort of makes sense. One of the other things that came out of this work was the ability to use hafnium and or zirconium. Just at Gossan Valley, you'll see yttrium come through as well, which basically we could use to fingerprint where the contact was between the hanging wall dacite and the rhyolite. And as I mentioned earlier, that's a really important contact to be able to pick out in the whole area. The process was repeated at Gossan Hill, and here you'll see that the dacite is actually a little bit thicker than the hanging wall dacite. Gossan Hill is a slightly larger, shall we say, ore deposit than Gossan Valley. You can see that the hanging wall anomaly, in this case, indium, bismuth, and antimony, is actually in aerial extent a little bit larger, but still hugging very tightly to that dacite contact mapped by, in this case, hafnium, yttrium, and zirconium. Also, again, we're actually seeing this southern base metal anomaly, if you like, and this is actually sitting more out into the hanging wall rather than just along the contact in this sense. So it was repeated at Scuddles. And of course, if you do something more than twice, it's not going to work the third time. And this is when you need a geologist who's worked on site for a very long period of time, who can just say to you, well, the reason Scuddles is different is that the dacite unit is significantly thinner. And the dacite is actually quite a good soak for metal. So when it's actually thin, it's not such a good soak. And so metal actually will tend to move further out and away. And I think that's what we're actually seeing here, with the pathfinder anomaly actually heading off to the north and again really hugging on that dacite contact with this side. But in this case, starting to actually look like it's getting into units within the footwall. However, the base metal anomaly again is sitting in that position in a sort of this asymmetric type thing that we're actually seeing in all the other deposits as well. So what did we learn? There's a bit of a summary. Basically, hafnium, zirconium, probably hafnium more than anything else, can map the dacite rhyolite contact. And that's that Golden Grove to Scuddles transition that we basically see as hanging wall, footwall. There's a distinct pathfinder signature of various elements, including bismuth, antimony, and arsenic, either in the hanging wall directly next to the mineralisation or potentially along strike from it from a short period away. We're seeing a lead thallium plus or minus zinc proximity anomaly, more so to the south, possibly associated with the zinc mineralisation. And also, we actually have to realise that the hanging wall dacite may not always be the soak for any sort of pathfinder signature, because it actually can get quite thin, like we were seeing at Scuttles. And one of the most interesting things for me was that the fact that even though a lot of these pulps were 40 years old, they were providing extremely robust data. A lot of the holes had only intersected mottled or ferruginous zone, but it appeared to be very few of the samples that were actually depleted in their geochemistry, or had actually just been transported material. With immobile elements, we could discriminate lithotypes, which is sort of what we're talking about with the hafnium, zirconium stuff at the top, but also, most importantly, the pathfinders were holding up in the regolith as well. However, alteration and doing anything with that was just not going to happen, because we are dealing with weathered rocks in this instance. So from this, we're able to basically develop a generalised geochemical model. And what I've done here is actually separate a model in terms of elements that could be used for distinguishing copper mineralisation in the hanging wall dacite or proximal position from possible zinc mineralisation as well. The ability to map that contact all the way through the field, particularly undercover with point sampling RAB, was just quite astonishing. However, it's only a model. So the question is, can you actually apply this to less well-explored areas and get some value out of it? So that means verification and whether you can actually generate some new targets. There's not much point in having a model if it's useless. So an area was selected to the southeast or south on mine grid of Gossan Valley, and the RAB pulps were retrieved and reanalysed. The Bassendean area was selected as an area of a blind test or proof of concept, and following on from some promising work from the Bassendean area, further validation occurred in the Cullens area, where we actually had some extra data from historic RAB, which there wasn't a lot, where there'd been downhole sampling, and some recent air core drilling with multi-element geochemistry. So in Bassendean, and I've left the orange dashed line there, which is my interpreted footwall, hanging wall contact, and you'll be pleased to see that there's actually some faults associated with that as well. Previously in this area, there was only 2 copper-lead anomalies known. With the new data from the 48-element ICPMS, bottom of the hole sampling, there was a lot more information to be gleaned. A number of hanging wall anomalies in terms of bismuth and then antimony and arsenic fell out immediately. The top copper-lead anomaly went from being 2-element to containing bismuth and tellurium straight away. The other thing you might notice in this slide, there's a lot of this pale green rock, which are these Proterozoic younger dolerite dikes and sills. Above these sills, there appears to be quite a lot of deep weathering and some transported cover, and I'll come back to that later because it's an important thing in the story. So from this, the interpretation was that there were 4 prospects or targets identified. That northern one, the copper-lead bismuth tellurium, with a hanging wall, antimony and arsenic anomaly. And then when we got the diamond drilling results, we saw there was a drill hole in that area of 5.6 metres at about 6% zinc and some quite healthy gold in it. The southern copper-lead anomaly with the bismuth actually had 6 metres at 3% zinc in it before it had actually been stoked out by one of these dolerite units in through the area. So both of them basically associated with mineralisation. However, the prospectivity of the antimony anomaly that's highlighted to the north and the antimony bismuth anomaly in the middle were basically 2 new targets that were generated out of that data set. In the Cullens area, again, there was new data. The interpretation of hafnium, yttrium and zirconium largely supported the original hanging wall contact, but much of the hanging wall in this particular area is intruded by dolerite. So to determine whether the rocks had actually intersected dolerite or not, mafic indicators such as scandium and chromium were added to the mix to actually work out what was going on. And there was quite a distinct concern that a lot of the true stratigraphy was being masked by dolerite. And that was in part because a lot of the signatures that we were getting appeared to indicate, or appeared to be quite high up in the stratigraphy. So where the contact had been interpreted, even though there is some mineralisation and Scuddles formation, there was a couple of prospects that seemed to be too far up in the strat. Fortunately, there was some old data available. It was, I would say, pretty cruddy, ICP, aqua regia, but of basically weathered rock. And in areas where we were able to interpret whether this was actually in hanging wall position or whether it was actually, as I said, worth following up. And we had that question over whether it was in the correct position. Adjacent to that area, there was mineralisation, so it was definitely worth pursuing. Sometimes things look quite different when you look at them in section. So even though the bottom of the whole geology in this area was dolerite and the surface mapping showed it to be dacite, the lith type in the logging showed it to be saprolite, weathered rock, but the second lith column was sandstone. So in this case, what we actually interpreted was that saprolite was probably developed on a footwall material that was quite strongly weathered. And even though we didn't have any multi-element new data on this, we could see that the barium, indium, copper, zinc anomaly was probably actually in the right stratigraphic position for mineralisation to develop in through there. So in this particular case, the bottom of hole lithology of dolerite may not have actually been representative of what the true material was that was sampled. In that same area, there was a new program of air core drilling done, and 48 element ICPMS was applied to it. Now, the logging from this wasn't exactly great or particularly useful because the material is extremely weathered down to the bottom of the hole unless you actually hit dolerite. So most of the other material was logged as clay and sediment. So applying what we'd learnt from the other samples and also integrating some stuff from some of the primary rocks and analysis that had been done on that material, particularly what we've learnt with the terms of the hafnium, zirconium and scandium, we're actually able to come up with a new interpretation of geology, picking out where the hanging wall units are and actually determining that the zinc that was anomalous within this particular section was actually identified in a favourable part of the stratigraphy. And the presence of moly adjacent to it was also considered rather intriguing. So in this case, again, a new target was identified by understanding the stratigraphy and the regolith and putting that into context of the geochemistry. Almost done. So what do we do? Well, systematic multi-element analysis of known deposits enable us to develop a generalised geochemical model. One of the great things we're able to do is to validate that with Bassendean. It was good to do a blind test. We could re-rate targets, but we were also able to generate a couple of new targets. In the Cullens area, where the hanging wall contact was masked by dolerite and weathering, we were able to actually start to work out what the hell was going on through there with the multi-element geochemistry. And it's just so important to be able to put that stratigraphic context to the geochemistry. If there was one big lesson from the whole thing, look, the real value is derived by integrating the geology with the geochemistry. For myself, working with Luke and the other geos on site, to be able to discuss these things, to be able to throw it up on the wall, for them to tell me I needed to go away and actually do it all over again was absolutely fantastic, as well as the ability to retrieve the material that was still around. So, look, I think there's huge amount of value to be able to be gleaned from historic samples. If you're not storing pulps at the moment, if you're thinking about throwing them out, you're probably going to, in the future, waste a huge amount of time. And that's why I would like to suggest, well, look, we have core libraries in Australia. I've been to ones in Canada, and I'm sure that there's other places that are actually storing drill core. Yeah, I know in I think I'm pretty sure in Finland and other places. But I think we need to think about something that I would call a pulp repository, because analytical techniques will actually get better. I mean, there's things like Fourier transform infrared that's going to become available, and various other machines that will give us huge amounts of information that we never even dreamed about in the next couple of years. So I think it's possibly incumbent on industry and government to think about extending their core shacks and libraries so that pulps can be retrieved. It doesn't have to be every single sample in the drilling program, but I think a really great representatives suite would be, a very great thing to be able to do. And I've got experience of that recently, having been down to Canberra to Geoscience Australia rock store there, where I was actually looking at offcuts from thin sections, the original rocks, and had access to the powders and crushed material of rocks that had been collected 50 years ago, which was just absolutely stellar. So my challenge probably to research organisation, government and industry is that they need to actually realise the enormous potential that reviewing and resampling of historic shallow samples can give to the identification of new targets and new mineralisation.